Hello, everyone, and welcome back to the channel. So, Docker, what is it? What are containers all about? And how do containers differ from virtual machines? What are the benefits of using containers? Now, if you're asking yourself any of these questions, you're in the right place. This video here will be focused on understanding containers. Before you start to learn the specifics of Docker or maybe Kubernetes, it's critical you have a good understanding of container concepts first. What are containers? Why are they so popular? And what problems do they solve? That's what this video is all about. By the end, you'll understand all these foundational container concepts. Then you can build on top of these on your way to learning Docker or Kubernetes as well. So we'll be keeping things pretty high level here in this video, and I won't be diving into any hands-on examples with Docker or Kubernetes or anything. But if that's something you're interested in as a part 2 to this video, or perhaps we do a whole series on Docker, let me know in the comments if that's something you'd like to see and how I can help. All right, so let's get started. Now, I'm going to assume that you have a basic understanding of virtual machines. And if not, just really quick, a virtual machine is essentially a technology that lets us logically slice up physical server compute resources like our CPU and memory. Hypervisor software technology allows us to assemble these slices together in the form of a virtual server or virtual machine. The benefit here is we can get a lot of flexibility with these virtual machines from many different infrastructure operational aspects. And then we can also pack a lot more of these smaller virtual machines onto our expensive physical server hardware and get higher utilization of the physical resources and ultimately get more value out of that physical server. Now, containers are similar, yet quite different. They aim to solve a set of challenges focused more on the software development and application delivery aspects. And then they also enable a lot of new paradigms in terms of application design and scaling capabilities. So let's start by looking at what kind of challenges may exist in the software development world. For application software to run successfully, there are a lot of pieces of the puzzle that need to come together to make this code work properly. First we'd have our application code, maybe written in something like Node.js. Now that code may be built on a specific version of Node.js, and therefore the code would have some dependencies on that specific Node version to run as intended. Then that code may have a variety of dependencies on other specific versions of other packages and libraries that allow the code to perform additional functions. Each of these libraries may have been built for a specific Node.js version to work properly. Then the library itself likely has a variety of versions that you have to take into account as well. Then all this stuff needs to run on a server of some type. And that server would have an operating system installed on it, something like Linux. That Linux OS can then be many different flavors like Ubuntu or Red Hat, for example, each of which would have different release versions. And those are made up of potentially hundreds of different software application packages that enable different kernel and software capabilities. And all those come together to allow us to run our Node.js runtime environment and run our application code in this example. So to summarize, for our application to run here, we have a bunch of different operating systems to consider. Then the release version of those. Then the release versions of potentially hundreds of different packages as part of that operating system. And then our code runtime environment version we're writing our application against, and potentially hundreds of different library dependencies. Now, if we think about a larger application architecture, your software component you built may need to interact with a database, or maybe some messaging queue or cache components, or maybe communicate to different parts of the application through an API. All these aspects have similar versions and dependency chains as well. All this stuff combined exponentially increases the number of items we need to consider to ensure our application will perform as expected. So I think you get the point here of the dependency complexity here and all the pain that this causes. There's a lot of pieces that need to come together to successfully run your application you built, but there's still even more layers of complexity with this. Maybe you built your software components on your Mac laptop running the latest version of Node.js, and the latest versions of all the libraries you pulled into the application. But what happens when you try to run this in production, or perhaps a Linux-based server running the Ubuntu OS that hasn't been updated in 6 months? Will that complex dependency chain still work properly for your app on that production host? Or will a version of something in that chain be the weak link to cause some issues? Now, what if you're working in a large team environment on multiple different projects? Maybe your development team has different laptops, all running different OS versions. Maybe your work projects are based on different versions of Node.js, or perhaps different programming languages altogether. How do you consistently and quickly switch between these different project environments? How do you ensure your code that works just fine on your laptop will work the same way when you share that code with a colleague using their laptop where the development environment isn't configured exactly the same way as yours? How do you ensure that once the development work is complete across all these different projects and you ship that off to your production environment, that'll run on those servers, making up that production infrastructure just like it does on your local laptop? So all these dependency and delivery workflow challenges are partially why containers exist. Containers allow us to package all our application code and all the dependencies together into a standardized image. Now, similar to actual shipping containers, these containers are essentially standardized units that can be loaded up with any number of items inside. The container items within it stay isolated from other containers and the actual ship itself. As far as actually transporting the container, we don't necessarily care about what type of ship it's on. We have no dependencies on the ship itself other than it needs to be designed to carry shipping containers. Where that container is placed on the ship and how many other containers are there along with it, we don't necessarily care. The ship can just take your container and run with it. Okay, this is great stuff. Containers sound amazing. But you're probably saying, Mike, I know about virtual machines. And aren't these sort of the same thing? Well, let's take a look at virtualization and containerization technology differences. And it may help understand some of the pros and cons of these different options. So with virtual machines, we have our physical server with some form of hypervisor layer that does the magic of allowing the virtual machines to interact with the physical hardware components of the host. It facilitates the creation of the virtual machines and provides that isolation of the VMs from one another. Now, as we have this raw virtual server, we still have all the typical things we need to do with it for it to provide some value to us. Otherwise, it's just a bunch of these carved up logical slices of the underlying physical host. So to make use of the virtual machine, we need to install an operating system on it. Now, this may be a Linux-based operating system or perhaps Windows. Whatever your use case, you'll need to install the appropriate operating system on the VM. Now, these operating system installs can be quite large, oftentimes many gigabytes in size. Now, if we start to think in a sort of large scaling mindset, say you need hundreds or even thousands of these VMs, the size of these OS installs can certainly add up quite quick. The waste with VMs in terms of the large OS installs repeated multiple times, then the extra overhead of the CPU and memory that VMs inherently create, plus the inefficiencies of the boot up time it takes to start a new virtual machine, all take their toll. In addition, you have the VM provisioning and the OS boot up time to consider before you can even actually start running your code. All this can add up to quite a few minutes before our application is actually ready to respond to incoming requests. All those inefficiencies of having the same OS software installed over and over across all the VMs, and the wasted CPU, memory, and storage overhead for the VMs, all adds up quite fast. So what does this scenario look like then with containers in the picture? Well, it's very similar. So taking a look at the stack involved with containers this time, we still have that same physical hardware layer behind the scenes. Now, instead of that hypervisor layer interacting with the kernel and physical hardware components, we install an operating system on the server. For our example here, we'll use the Ubuntu flavor of Linux. So we have our physical hardware, the Linux kernel, then the Ubuntu operating system installed. Now with containers, we need some type of container runtime engine installed to actually run our container images on this host. Now there's a lot of container engines around today, but a common container engine is called, as you can guess, Docker. This container engine, like Docker for our example here, performs all the magic to interact with the kernel layer on the host, to start the container process and have that interact with the host hardware components like the CPU, memory, networking, and storage, and also isolate the containers from one another. The host operating system and kernel layer become shared across the containers that may run on it. Now, for our example, say our container has our application code and the Node.js runtime and all the various libraries and dependencies and tools all bundled in. And then we run this container, and the container engine allows the container to interact with the underlying host operating system and kernel to start running our application. We're not waiting for a complete operating system to boot up here when starting our container. We just run our container, and it can start executing our code or application processes as needed. Now, if we go back to that scaling conversation, if we need to run 200 of these containers, we don't have that overhead of running 200 virtual machines with all the large OS installs and likely very underutilized CPU and memory resources. Depending on the configuration of the container image and the host machine's resources available to us, we could possibly run all 200 containers or more on the same host with essentially none of that storage bloat of the full OS installs for each one. Then we also have the potential to significantly reduce any idle CPU and memory resources on the host, maximizing our value we're getting from it. So we compared virtual machines and containers a bit, and we should have an understanding of some of the differences at this point. But what actually occurs these days is a combination of both these technologies. So today we often take advantage of the flexibility and convenience virtual machines offer us, but then we run containers on the virtual machines. So to start off, we always have some physical server in the background here. And this is of course true for your traditional data center environments and cloud environments as well. Then we have our hypervisor layer that lets us create and manage virtual machines on this physical server. Then we create a virtual machine running on that server. Then within the virtual machine, we install our OS we need, like some form of Linux. Then we'd install our container runtime like Docker. And then after all that, we'd finally be able to run our containers. With this containers on VMs type of technology stack, at the infrastructure level, we have tremendous flexibility in our environment by utilizing virtual machines. Then we can also take advantage of all the benefits that containers offer us by providing those standardized application components we've packaged up along with all their dependencies so our code can run as it was originally designed to do. Now, another important aspect of containers to bring up is that containers embody the DevOps methodology as well. So we can, create or update our code, package the changes up into a new container image, and then run that standardized container image through some automated testing environment pipeline, and then deploy it into our production environment confidently, knowing all the necessary components are within the container itself. We're much less concerned about that crazy number of dependency variations that could exist between our development environment we had on our laptop compared to the test environment, and then moving that into production. Well, I think that's going to be a wrap for the scope of our video here. I hope you found this a good introduction to what containers are, where they differ a bit from virtual machines, and some of the benefits they provide and where Docker fits into that picture. Now, please let me know in the comments if you'd like me to dive into containers and specifically Docker in future videos. I'm just starting out here with videos on the channel, and would really appreciate your comments on what you liked or what I can do to improve future videos, just so you can get more value from them and help build your cloud and DevOps skills further. I have lots of great lessons planned soon for the channel, so please take a moment to like, subscribe, and enable those bell notifications. It'll help the channel grow and ensure you get the latest notifications so you can keep growing your cloud and DevOps technology skills. With that, thanks again for watching. Keep that learning voyage going strong, and I'll see you next time.